Yeah, welcome to my talk on bridging the gap, how to go from exploration to production, especially for deep learning models. Just a short introduction of myself. My name is Marcel Kurovski. I'm a data scientist. I work for ONNX, and in the meantime, while I do introduce myself, feel free to go to the blog post I wrote about that topic, which covers all these things in a 2-series blog post, or just check out GitHub, where I put on all the code that is related to that investigation or that work I did there. I'm originally an industrial engineer and have been focusing during the last 2 years on deep learning and recommender systems, especially the combination of both things. So I was developing a deep learning-based recommender system for mobility, which most of you might have heard of. And this was when I first crossed the path of, hey, there's a nice POC. How can we go further and bring it into production? So what is the whole pipeline of an idea to the end where the idea or the concept and the final model serves people's needs? Just a few things about ONNX itself. So we are an IT project house. I work in Cologne. We have different offices across Germany, so in Munich as well as in Hamburg. Originally, we are from Karlsruhe. This is also where I studied, but didn't like it anymore. This is why I moved to Cologne, and I'm pretty happy with that decision. So we do all kinds of software development, data science, where I personally work for, and IT operations, so we cover also the whole pipeline. Okay, so much to the advertising. Now let's talk content. So this will be my agenda. A lot of things. I will try to cover them within the next 30 minutes. So first, I will give you some motivation, why I decided to go for the topic, show you some technologies that are out there. It's not a full covering, but I hope that they can be regarded as to be the most important ones. Then show you 3 small approaches I tried out and show you the results of, which then try to bridge the gap from an explorative task, going into the data, and then going into the model that kind of solves the problem, translating these models, and finally deploying them in a production-oriented environment, which I then will finally compare and show you just the outlook and some further concerns which appeared during that research. Okay, let's start with the motivation. So what I experienced within my journey across machine learning in general and deep learning in particular, going into recommender systems, is that there's a great variety of proof of concepts, of blog posts. Hey, I used MNIST on that data set, and this was the accuracy I got from. I wrote a blog post about this, and so on, which is pretty good for people who like to start with it and easily want to grasp how the inner workings are and want to do something, because this is maybe how people learn best about doing it themselves. And most of it is about exploration. But what I also see is that there is a magnitude of scientific publications, and there's not that much concerns about how to deploy things, how to go down the whole pipeline. And what's also lacking is the interoperability between networks, or not between networks in particular, about general how frameworks are linked together. So it's a big domain. There are many frameworks across different programming languages. But what I feel is that how to connect them with each other is not the biggest concern. And there is also that person you might know, Andrew Ng. He coins the term of AI being the new electricity. And whether or not you are going with that, there's some kind of analogy which I based this whole structure on, which I like. It's when you look to electricity, you have some kind of 3 components, which brings electrical energy from the consumption side, from the production side to the consumption side. And this is generation itself, it's a transmission, and finally it's a consumption in the households or in other areas. With kind of artificial intelligence or machine learning models in particular, it's kind of similar. So we do some kind of model exploration. We generate some insights, some ideas, some approaches to solve problems. Then we somehow need to translate them if we don't like to stay within the same framework where we did our exploration, because this framework might not be the best one to do the later deployment or production part. So, and this is also the analogy I like to go with throughout these approaches I'm going to mention. So if we take, for example, a few technologies within the model exploration domain, you have worked with TensorFlow or might have found PyTorch to work easier, especially for beginners, but which becomes more and more powerful. And there are others like MXNet or Keras that is built on top of TensorFlow and works as a kind of wrapper and makes things easier. But also sometimes it makes things harder to debug, where kind of PyTorch plays out to be very, very good because it gives you that pythonic way of seeing things, of debugging, and of failing quickly, but therefore also to learn quickly. In terms of model translation, the frameworks are even younger. So a few of you might have heard about the Open Neural Network Exchange format that was just released last year, or the Kronos group published NNAF. And on the deployment side, we talk about Docker, Kubernetes. We can also go for rather hobbyist approaches, building our own web service, or use predefined solutions with GraphPipe that just popped out by mid-August of this year, or using TensorFlow Serving. So there are some solutions on the exploration side that also offer capabilities on the deployment side. OK, what I did was just to pick out or build 3 of them. But I would like to see more and more of these combinations that kind of bridge the gap and go from exploration to production. So what I first want to show you is a model I'm creating in PyTorch, which I'm then translating using the Open Neural Network Exchange format, ONNX, and then using GraphPipe, which offers me a Docker container and different model server implementations. The second one takes the first 2 approaches and keeps them, but we are going for TensorFlow Serving. And the third approach will be based on, let's do that all by ourselves. Let's build our own web service that kind of wraps that trained models and offers them as a REST API. And finally, we can go further with these. We can deploy them in the cloud and make them queryable by people and serve them and make them useful for someone out there, and not only for ourselves or for our own explorational demand. But there's something lacking. It's data. So let's first have a look into that one. Because the whole thing rather not starts with model exploration, it starts with data exploration. And there you might have heard about MNIST, which is some kind of the hello world for data science, but there is also MNIST, which is quite a far bigger data set because it does not only cover the 10 digits, it covers also letters, upper and lower cases, and it's also quite new. So I think that popped up in 2017. There's a paper which covers the details of that data set, and I found that more interesting because it adds some more diversity to the community who is working with these things. This is why I decided to go for that data set. So, and yeah, what we can see here are, as I said, the different letters and digits. And it's kind of very unbalanced. So looking into these 800,000 examples, half of them, so 10 out of 62 classes, cover 50% of the whole data. And for the upper and lower case, they are quite balanced compared with each other, but among themselves, they are still even unbalanced. And I won't cover that much the details on how we can get our accuracy up to 99% or something like that, because what should be our concern here is how to move doing a model and going further with it and to bring it into production. So therefore, going into the model exploration part, I started with PyTorch. Originally, when I jumped off my data scientist career, I was going with TensorFlow, which is kind of the most widely used networks out there, and they're about to publish their version 2.0. And PyTorch, which is supported by Facebook, so also some great supporters there, like Google for TensorFlow. has just pre-released its version 1.0 with even more capacities as it had before. And what is pretty nice about it and what kind of distinguishes it most from TensorFlow is that it adheres to the dynamic graph paradigm. In TensorFlow, you have that static graph paradigm, so you kind of define a computational graph that embeds your model, and you need to define it every time from the beginning. And here in PyTorch, you can kind of adapt it dynamically and can directly look into, for example, the tensors, what numbers they are holding, and also use it for quick debugging, which is sometimes hard in TensorFlow. This is why, at least according to my opinion, I would say that PyTorch is easier for beginners, but it's still becoming more and more powerful. So it's easy, lightweight, and intuitive. And there's also a good point, it already integrates with ONNX. So it's possible to just export your models in an ONNX format using PyTorch. And just mentioning TensorFlow Serving, we hope to expect the same for them. They are still quite fuzzy on that topic when they made their release notes to, not the release notes, but the announcement of TensorFlow 2.0. But I would at least hope that they are also going to support ONNX, which then kind of could become an industry standard for models that are saved in a generic way. So let's just quickly cover the model exploration tasks. So we generally have a definition of a graph, which we have here. So we just create a new model, and therein we define our functions that are then applied to the data stored as tensors. In the next step, we create the model instance. We create a loss that we want to minimize and an optimizer that is responsible for adapting the variables in order to minimize our loss. And then we have our training routine. So far, so good. So just a few lines of code, and we have our all set to train our model. So let's do it. And it works pretty good. So roughly 2 of 3 cases we can classify correctly. So that looks quite good. But maybe we can go better. This is about the exploration. So once you start off with a model and try to apply it to data, you kind of learn what you do wrong, what you do good. So you might have a look into the confusion matrix and see what letters in particular you are failing classifying correctly. And you learn more and more. But then you also want to apply what you learned to a new model and see how well that performs. And as I said, this is quite easy. So you just adapt the modules, and then you go for a second routine. And yeah, as sometimes in all these cases, adding layers adds complexity to the network, which then also advances its capacity to capture the underlying the underlying structure between input and output data. So let's just add a few layers. So, and that also already gets us better. So we make almost a jump of 10% in accuracy. So we are almost classifying correctly about 80% of the data set. Quite good. But staying with Pareto, we stop here and go for the next point. So, and this will be ONNX. And why that? Because in PyTorch, we currently don't have that good the capabilities to productionize the models, but we have them, for example, in TensorFlow with TensorFlow Serving. So there's a gap. There is a gap between 2 frameworks. We want to use the one for deployment, and we want to use the other one for exploration. So how do we go from one to another? And ONNX kind of fills that missing link. It is already supported, widely supported by Amazon, Facebook, and Microsoft. It's quite new, so it exists since 2017. And there are these frameworks mentioned here. So for example, PyTorch, MXNet, or the Microsoft Cognitive Toolkit that integrated the ONNX capacity by such that you can directly export the models from within the framework. And there are also some connectors. As I said, TensorFlow is quite important. So it doesn't support ONNX by itself yet, but there is a connector for it that then allows you to also create a TensorFlow model representation from a generic ONNX file. And this is what you can see here. So we have our trained model, our deep neural network with the 3 layers that performed better. And here we just call our torch ONNX export function, and then we pass it our deep neural network model. We also pass it a path where it should export the model file to. We can do some annotations, so how do we like the input, the output, and the layers, not the layers, the weights and biases to be described. And what we also do, and this is kind of specific about ONNX, it works via tracing. That means it exports a model by executing it. And this is why I kind of need to provide it with an example input. In this case, this is just a flattened random image. We pass it to our export, and the export itself creates one forward pass, and by that sees which operations are called, records that calls, and then exports it into the generic representation. And we are done. We have a generic representation of our model that we can now use in different frameworks, that now is kind of framework independent. So this is why we can directly move over to deployment. And regarding deployment, I just showed you there are at least 3 strategies I went for here. There's a multitude of different you can go for. The first one I would like to cover is GraphPipe that just popped out as of August this year. It was published and made open source by Oracle and implements different model servers, among them TensorFlow Serving. But what they do in addition is they don't adhere to the standard configuration of TensorFlow Serving. They kind of tweak it in order to achieve a better performance. And instead of using the protocol buffer format, which TensorFlow uses for the serialization and deserialization of data, they use flat buffers, which then adds some more efficiency to their implementation. And they also offer client implementations, which you can then easily use to fire REST queries against your web service. And this web service within GraphPipe can then be served as a Docker container, which you then can just horizontally scale, for example, by using Kubernetes. And this is how the structure looks like. So as I said, there are different servers that are implemented, and they integrate with ONNX. So this gives you a nice thing on top to try and productionize your model. OK, so how do we do that? At first, I was trying to use the ONNX model server itself within GraphPipe. So we used PyTorch for the model exploration part. We translated our model, and now we like to serve it within GraphPipe using its ONNX server. So what we do for that is we do not only have to provide the exported generic model file. For that way, we also have to kind of provide a JSON that is describing how the input for the network looks like. At least this is what I got from their documentation, which is still unfortunately pretty sparse. So I went for that. I just tried to run the Docker container, and I failed. Because we have some kind of a size mismatch. So these 784, they look quite as we would have expected, because this is kind of our flattened input dimension. But on that side, this looked kind of fuzzy to me. And also not being confident with Caffe 2 as well was where I said, OK, also after doing some search, I couldn't really solve it. So there you might still see that this is kind of a premature network. So it's a great idea, and but on that hand, it might not work yet. So this is when I went for another solution. So this does not work, but as it implements different model servers, let's directly move over to TensorFlow Serving within GraphPipe. OK, so let's use that one. And here comes into play the great advantage of the generic model representations, because I could just use that ONNTF, so the TensorFlow connector for ONNX, that provides me with that prepare function that just takes our generic model representation as input and transforms it into the well-known protocol buffer format TensorFlow uses to serve or not to serve to save its networks. So now we just went from a PyTorch model definition into a generic one, and here we have the same one just in the TensorFlow world. And now, also within a few line codes, we can use all the advantages that TensorFlow provides. And this is what we do here, but just within GraphPipe. So let's again try to start that model server. So we just provide it with our model, which TensorFlow Serving should serve within GraphPipe within the Docker container. And great, that works. So we can now fire queries against our port 9000 and hope that the classifications look similar to what we trained on. OK, so this is the first way, going with GraphPipe. Let's try another one. Let's go for TensorFlow Serving directly. So TensorFlow Serving is already a little older, because I think already in 2016, when I did my first steps with it, it was already there. And they have kind of a, quite comprehensive structure, but also with some great ideas. So at the center of TensorFlow Serving, you have the dynamic manager. The dynamic manager kind of manages the lifetime of a model. And when I talk about model, they rather talk about so-called servables. Because a servable might be part of a model. It might be just a full model or something like that. And we just define a path or a file system, and within that a parse, where we save our models to. And every time we save our model there, that file system notifies our manager, hey, here's something new that you should be notified about. Try to load it and try to use it for serving. And then the dynamic manager lets it create a loader instance that just notifies the manager, hey, I'm ready to load that model just when you are ready to allocate that resources to me. And this is when the dynamic manager just does the balance between its main job, which is serving client requests, and about additional jobs, which is kind of handling different models it has loaded, or about, hey, there are new models, may I load them? And when the dynamic manager then decides, OK, I have enough resources I could allocate for the loading process, the loading starts, and the version becomes kind of an expired version of our model. So this is when we load our model and can start serving from that. And also, regarding the version policy, we are able not only to hold a single, the most recent version of a model, we can also hold separate versions of it. And by this, easily, for example, do A/B testing or other evaluations we want to run on the data, or have the ability for clients to specify a specific version of a model they want to have a response from. So this is how TensorFlow works in general. Now let's use it. So for that, there are kind of 3 steps you need to go with. First, you need to kind of provide a proper signature, which is shown on the right, that just kind of details on how does the input look like, how does the output look like, and what kind of method am I taking on. So this adds some verbosity here. When we are finished with that, we, of course, need to export our model using our saved model builder. And then finally, we can start serving it, as shown here. So we save our model into a specific folder. And this folder is then supervised by the manager, meaning that every time we save new models to it, it allocates resources and jumps over and does that hot shift over to the new model. OK, let's show, or let's just see what the third option might be. So there I just started doing the whole process myself. So using Flask, which is a very neat and simple package in Python, which allows you to create a web service. So it's based on Werkzeug and Jinja 2, a template engine. And what we did there is we have our model again. and we also use TensorFlow, but we somehow need to wrap it, because TensorFlow always executes a model within a TensorFlow session. So we need to somehow wrap that session, and within it, our inference process. I built a really, really minimalist front end, so please don't judge me on that. And of course, then the final web service with Flask that then manages the requests and, of course, hopefully sends the response back to our clients. So in that case, that might look like that. So as I said, it's pretty dirty, but it at least does the job. And yeah, if we provide it with an image, okay, it tells us what was the detected class, and furthermore, it also shows the softmax distribution, so how confident it is about the different classes there are for classification. Okay, but how do these three approaches compare with each other? And which one should you go for? And how effortful are they? For that, I just tried to do a short benchmark, concentrating myself on throughput. So what I did is I sent single instance requests to my 3 servers that were served locally. So I also deployed them to a Google Cloud instance, but even due to sometimes poor internet connection, this might kind of influence my results. And this was why I also tried it on my local machine and raising local web service. So all of the results you will see in the following are based on that local comparison, the local benchmark. What I tried to capture is just the end-to-end throughput, so the whole process it takes for serialization, deserialization, inference, and the transport of data. Because, as I said, GraphPipe implements some kind of other solutions, the flat buffers, to do that serialization and deserialization steps, where TensorFlow goes for protocol buffers. This might be a difference in here, and this is also what Oracle claims to be the case. So let's look into the single inference case. So as I said, there is no batching involved. So every time I send a request, a REST request to my web server, I just send one single instance and let it classify it. So and what we can nicely see here is that TensorFlow Serving kind of excels in that task, and yeah, kind of serving 200 requests per second successfully. Second point is TensorFlow Serving embedded into our GraphPipe, and kind of expected Flask performs worst. But still not that bad compared to what we would have expected from GraphPipe to be the case. But you can also go for another way and try to batch requests. So this would be something you could do in production systems and see, okay, I just wait 10 seconds, I just wait for 10 millisecond window, collect all the requests I receive within that window, create a batch of 100 to 200 requests or something like that, and push them collectively through the network, which then makes use of all that matrix multiplications, and yeah, is kind of a more efficient way of inference as to do it single instance by single instance. So I also went for that, and I adhered to what GraphPipe did. So this is the case for batch inferences. So if we are going for 120 examples every batch, then GraphPipe stands out a lot. So it's almost approximately 3 times the throughput that TensorFlow itself can handle, just by using a pretty much higher batch size, which then might go back to the way they handle the data and implement the model server itself, because they claim to also optimize the parameters that TensorFlow works with. And as we see, we're quite successfully with it. And at least this was also quite consistent with what they claimed on their documentation. So they also tracked the end-to-end throughput and were quite successful with their GraphPipe solution. So you have to compare the blue bars against mine, because I also just went for the concurrency for the non-concurrent case. So just using a single instance, a single client instance that fires query sequentially against my web service without any parallelism or without any asynchronity. Yeah, so we see it's quite consistent. GraphPipe also does a great job. So what can we conclude from that? So what I experienced is, at least regarding the implementation effort, GraphPipe is at least the best among these three. So it kind of separates all the signature definitions that you, for example, need to do for TensorFlow. You just have these provided Docker containers that come with, for example, a optimized version of TensorFlow Serving. TensorFlow Serving, as you have seen with that signatures, you need to define is a little more verbose. Flask, of course, is the most verbose solution if you want to do it by yourself. But at least it's kind of more understandable. So if you really want to go into how these things are interconnected with each other, how do they work, then this might be a way at least to explore that. But if you like to go for really productive systems, then maybe rather adhere to TensorFlow Serving or GraphPipe, at least when you take these three things or approaches into consideration. What did we see about the inference? So we see that GraphPipe is pretty good when it comes to batch inference. But if we have single instances that come into our system, then it might not be a good choice. And yeah, this of course might also be some concern for production systems where I'm not batching on my inference requests, where I could like handle them single instance by single instance. And then in that case, at least I would rather not go for GraphPipe, at least in that case. Yeah, so this is at least the conclusion, and I hope that regarding the whole domain of interoperability, there will be further frameworks, especially TensorFlow, hopefully supporting ONNX. And I also hope that kind of end-to-end data science, so taking production into account when starting with exploration, so at least the whole pipeline becomes more and more an inherent part of the community. And I hope that this is at least a tiny contribution to that. And with that, I want to conclude and thank you for your attention.